I am very happy to welcome you all to today's commemorative lecture on the occasion of 125th birth anniversary of the eminent scientist Meghnad Saha. Meghnad Saha is a great scientist known for his ionization equation. He has done a lot of other work also, one of them being reforming Indian calendar. Today, we have with us Professor Lokanathan, retired professor from Rajastan University, Jaipur, to tell us about Saha as a physicist. Professor Lokanathan is an acclaimed teacher. His association with us goes back to 1990s. He has taught in our REAP program and was instrumental in stabilizing that program. For us, he is very special. He has been supportive of all our activities and has been a well-wisher of the planetarium. A hearty welcome to you, sir.
So Professor Lokanathan completed his PhD from Columbia University, just for the record, and he taught most part of his career at University of Rajasthan, Jaipur. And there are very few researchers who are very good at both researching as well as in teaching, and Professor Lokanathan is one such rare personality who is a fine researcher as well as a fine teacher. It is said that the greatest form of education is to spend some time alongside a wise man, and to spend 2 decades with a wise man is not a small time for us, and his influence on us, all the student community in the planetarium, me included in this prestigious group, we have immensely benefited from his wise methods of understanding physics, understanding nature, and we would like to take this opportunity not only to introduce him but also to thank him for all the influence that he has had, positive influence that he has had on all of us. Is that he shares one common feature with Meghnad Saha, about whom he is going to speak. Both Meghnad Saha and Professor Lokanathan have co-authored a book on thermal physics, which some of you would have seen. And of course, his quantum mechanics textbook, co-authored with Professor Ajay Ghatak, is legendary and very well known to all undergraduate students.
You see, Babulal Saraf, whom Madhusudan mentioned, was my senior colleague. He and I were professors in Rajasthan University. He was a few years older than me, and he was the really prime motivator of all the experiments, some of the experiments that you see here. But I also had a hand in it. And Babulal and I once were attending some national conference, I think, in some place, physics conference. And during a break, we used to gossip like youngsters would. At that time, in those days, we were young. And some of the younger scientists who were very brilliant were probably slightly irreverent towards the older generation. And Babulal said in chaste Hindi, "Arey bhai, मैं तो उन्हीं को बड़े वैज्ञानिक मानता हूँ जिसका नाम टेक्स्ट बुक में छप जाता है." And he mentioned 3 names: Raman effect, Bohr statistics, and Sahas. And in retrospect, by the way, there were other great names also whom I'll mention, but these 3 were more or less contemporaries. Raman was the oldest, slightly older, and S.N. Bose and Meghnad Saha were classmates for many years. And there is, in retrospect, I'm a Tamilian, and I will tell you, there's a Tamil saying, when somebody makes a wise remark, "Avan vaayila shakkara podano." What is the Kannada equivalent to, put sugar in his mouth? So I consider that should be a good introduction to Meghnad Saha. He has been in the textbook, right? Like the other grades. All right. Now, by the way, how do I get to the video?
If you just press this, it goes to the next slide.
And that's the trio, all right? You recognize them, or do you want me to tell you Raman on the top left, and the top right is S.N. Bose, and the next one is Meghnad Saha. By a curious coincidence, not coincidence, by a curious thing I want to tell you is, it so happens, although I am going to talk about Meghnad Saha, I never met him, all right? But I met the other two. And what is more, I spent some time with them. So, Professor Raman, when, I met before as a postdoc in 1957, I went to Oxford, and I spent half an hour with him, or 20 minutes or something, or a little more than that. And I think it was a good thing in order not to go away with a swollen head. And if you spend 25 minutes with C.V. Raman, then you won't get a swollen head, I assure you. Okay? And Meg and S.N. Bose, very many years later, I had occasion to bring him to IIT Delhi, where I was teaching then in 1964. And I spent 2 hours with him, talking to him and so on and so on. Meghnad Saha I never met. But I knew a great deal about Meghnad Saha, because Meghnad Saha's students, I'll come back to that, one of his students was my professor anyway. Meghnad Saha was born in 1893 in Narayanganj district, in a place in those days called Dhaka. Now it is called Dhaka. D-H-A-K. In those days it was called D-A-K-C-C-A, anglicized name in the British days. And his parents were not particularly well off. They were not destitute, but they were not well off. Saha very early showed 2 traits which were to stand by him right through his life. Number 1 was obviously his brilliance. He was brilliant right from the beginning. You could see he was a brilliant lad. The second one, very important, was he showed a strong spirit to stand for justice and what he thought was right. And even at a young age, he could stand up for it, and that got him into trouble in school. He was in a school called Collegiate School, Dhaka Collegiate School, and I think the one story is that he took part in the Swadeshi movement, and they didn't like it, and he had to leave the school anyway. Another one, I'll skip that story. Whatever it is, he finished his education in Dhaka and went to college. Now, all right, why did he acquire this great feeling of standing up for justice and all that? You see, one of the possible reasons is my guesswork. I'm not, if I were a historian, I would have gone more in, now I'm too old to do this. One possible reason is Dhaka was a hub of textile in the early days. Dhaka was a great place for textile industry. In fact, a huge percentage of exports came from Dhaka, very fine cotton, Dhaka Malmal and all that. Dhaka Malmal is a very fancy version of muslin. And the Industrial Revolution, beginning around the 1830s, the second Industrial Revolution, shifted the factories to Lancashire, and the industries collapsed, and particularly Narayanganj area and all those areas were driven to poverty, and it must have made a great impact on the spirit of our young lad Meghnad Saha, which stayed right through. And mind you, this is my conjecture, all right? Now, all right, now let's go to the... This is Dhaka University, by the way. And you may wonder, Dhaka University, how was it like? It was very famous even in those days. When I was a schoolboy, my father was a reader in economics in Madras, and he used to send me in Madras. He used to send me to collect answer books in economics from Dhaka University. And Dhaka University was a very fine university. It had already... And K.S. Krishnan spent some time in Dhaka University, and so on. Now, this is Presidency College, Calcutta. 1911, he went to Presidency College in Calcutta, did his BSc in mathematics, finished it in 1913, MSc in 1915, by which time he was quite brilliant, sailed through. MSc was probably in applied mathematics, and immediately I'm sure he could easily have got a scholarship to go abroad, as many people did. Why didn't he do it? Because it was the war, the First World War, and he couldn't go abroad. And instead he did his PhD. He was to do his PhD in Calcutta, but before that he became a lecturer in 1916 in the University College of Science, which was founded only 2 years before by Ashutosh Mukherjee, a great name which you will hear about. Ashutosh Mukherjee founded this with the financial help of Taraknath Palit. Palit is a great name with which C.V. Raman was also to be associated. He was a Palit professor. Later on, Meghnad Saha was going to be a Palit professor after Raman. And a person called Dipendra Mohan Bose, I'll come to that. So, then, 1918, he got married. In 1919, the First World War ended, and Dipendra Mohan Bose, who was a nephew of Jagdish Chandra Bose. How many people don't know about Jagdish Chandra Bose? You all know about him, right? Jagdish Chandra Bose had founded an institute, and Dipendra Mohan was his nephew, who was to succeed J.C. Bose as director, and he served for a very long time. And Dipendra Mohan finished his PhD in physics. He was already a professor before he left for his studies, already a professor in Calcutta, and he finished his doctorate and stayed back in Germany until the end of the war. He couldn't get back. So in 1919 he came back as Rash Bihari Ghosh Professor in the University College of Science. All right. And eagerly, Meghnad Saha and S.N. Bose, a bit younger than Dipendra Mohan Bose. By the way, you may wonder why there are so many Boses. Huh? Well, I don't know. But if you change your name to Bose, I think chances are you'll get there. For some reason, all the Boses did very well. Many Boses did very well. Anyway, Dipendra Mohan Bose was a bit senior, and he told Meghnad Saha and S.N. Bose what was going on in Germany, what were the topics of interest, etc., etc., and this excited them. And the two did different things. S.N. Bose did something which I will come to soon, and Meghnad Saha did something else. And it turns out Meghnad Saha submitted an essay for what was called a Griffith Memorial Competition. Those were days. Even Clerk Maxwell, you have heard of Clerk Maxwell? Clerk Maxwell, in his time, long ago, 1840, 1850 or something, Clerk Maxwell submitted an essay competition, writing a scientific paper, and won a prize. That's how he made his name as a young man. So those were days when people used to write scientific papers for an essay, for a competition. The best paper would win a prize. So this prize was called Griffith Memorial Medal or something like that. And one of the judges was Devendra Mohan Bose himself. But the competition, the essays were to be submitted under pseudonyms, not their real names, because the judges were supposed to be unaware of the who did what. And Meghnad Saha submitted the paper under the name Heliophilus. I am told Heliophilus is some butterfly or something like that, biological thing, but I strongly suspect that's not why he chose the name. This is again my guess. Helio is sun, and it had something to do with his choice, whatever it is. He submitted it, and very soon it became clear it was a great paper. And the paper title was nothing less than Origin of Lines, Lines, Origin of Lines in Stellar Spectra. That was the title. All right? And it was very soon published in the in Philosophical Magazine. Later on, a year later, Proceedings of Royal Society also. But the first paper in Film Mag carried the title on ionization in solar chromosphere. All right? Solar chromosphere is one of the inner layers, not quite the innermost layer, etc. And this is the paper that plummeted him into international recognition. Why? I will go into that. That is the last part of my lecture, in which I'll tell you a little bit of the physics. Right now, I'll go through the biographical information. Is that okay? All right. So, in 1920 and 21, Saha went to Germany and England as a postdoc, and when he returned in 1921 as Khaira Professor in the University College of Science. And he was a professor only for 2 years. 1923, he went to Allahabad University as Professor of Physics, and there he spent 15 years, during which time he also was elevated as a Fellow of Royal Society. Very young man, you must remember, 1893, and he became a Fellow of Royal Society in 1927. He must have been hardly 32 or so, all right, or 33. All right, now, in Allahabad, this is a picture which shows sitting down is Meghnad Saha, J.C. Bose and J.C. Ghosh. S.N. Bose is standing up and so on. And Madhusudan, I must thank Madhusudan, who has put together many of these lovely old pictures. It shows the kind of, garments they were wearing. They were comfortable with these things. Sure, all right, they were great scientists, and this is how they were. All right. On the left, you have S.N. Bose. In the middle, you have Meghnad Saha. And on the right is a chap called P.C. Mahalanobis. How many of you have heard of him? Good. He was a bit senior to all of them. In fact, Mahalanobis, I think, even interacted with the great Ramanujan in Cambridge. He was a bit senior. So the reason they are together here is because by now Meghnad Saha was widening his interests. So he was advising people, well, I will support Mahalanobis. I entirely agree with Mahalanobis for establishing the great statistics institute. Planning is important, etc. I'll come to that in a minute. All right. Now, in Allahabad, he had three. He had many students, I'm sure, but three of the names, Professor Diaz, they are important because of my association with them. Professor D.S. Kothari, you've heard of him. He was the chairman of UGC also for some time, but at that time he was a young man, and he later on, Professor D.S. Kothari was a student of Saha, Professor R.C. Majumdar, Professor P.K. Kichlu. All three of them joined as professors in Delhi University in slightly different times. And they were professors when I was a student in Delhi University in the late 40s. All right? And that's how I came across them. And it is through Professor D.S. Kothari. He died in Jaipur. I will come to that. In the last 2 years, I spent a good deal of time talking to him, because 93 he died, 1993. 1991, 1992 and 1993, he used to send for me, and he was not very well, and I used to go sit with him and chat about all sorts of things, but that's another story. And he used to tell me about Meghnad Saha. All right, so, and this is again S.N. Bose. For one, that's a boson, all right. What is that peak, Madhusudan?
That's the condensate.
Ah, so that's a much later affair. All right, it's a boson condensate. Don't ask me now, maybe later. This is Professor D.S. Kothari, the student, my professor, the chairman of UGC, etc., who died in 1993, and a stamp was issued. And by now his interest had widened, and he wanted to promote, Professor Meghnad Saha, he wanted to promote Indian science research in various institutions in various ways. That was one passion. And the other passion, he had many passions. Madhusudan sent me a marvelous talk by Devendra Mohan Bose about Meghnad Saha. After Meghnad Saha had died, he gave a talk, and that's a beautiful talk, and he should know more than me, certainly, Devendra Mohan. So if you're interested, you can get it's available on YouTube or something, you can get it titled from him. So I am indebted to this talk also, and his interest widened, Meghnad Saha's. And the second, he mentioned many other things, but I will select only two, apart from the research interest. He was also very much interested in using science for economic and social development in this country. That was a passion for him. That is, so already in the 1930s, the subject, he was already it was becoming clear to him that nuclear physics was going to be a very important area. Neutron was discovered in 1932, and until the neutron was discovered, there was no nuclear physics, okay? So it was only after that, but very quickly, Saha became aware that nuclear physics was going to be very important. So if it was going to be nuclear physics, and by the way, he established a syllabus for nuclear physics, and I'm going to talk about Saha Institute of Nuclear Physics very soon. But why is your Department of Atomic Energy, as it is called, why not nuclear energy? Because for strange reasons, the ignorant people at the end of the Second World War, they called it atomic energy, right? strictly speaking, atomic energy is what you get when you turn your gas on for cooking, all right? That is atomic energy. So nuclear energy is what is now known as atomic energy. Anyway, it doesn't matter, it's only a name. So atomic energy, there was a committee in CSIR already for developing atomic energy, and one of his passions was to shift atomic energy to Calcutta, make Calcutta the base and so on. And somebody else stole the game from him. But they were friends, but there was good, healthy competition, and atomic energy went to Bombay. With whom? H.J. Bhabha, all right, and Tata and so on. That's another story. It shifted to Bombay. However, there was a good deal of activity, and this is the foundation stone laid down, but I'll come to that later, all right, just a little later. So in 1938, he returned to Calcutta as Palit professor, succeeding C.V. Raman and Devendra Mohan Bose. So then he became Palit professor and stayed as Palit professor very nearly until he died, I think. And in 1944 or so, he had helped acquire land in Jadavpur near the university for shifting the Indian Association for Cultivation of Science, that's where it is now, and so on. So he did a lot of these things, activities, helping the growth of science. In 1949, there was the foundation stone, that is the picture you are seeing, laid down for the Institute of Nuclear Physics, 1948. That building was established with the blessing of Nehru and the money of J.R.D. Tata and probably a few others. And it is now called the Saha Institute of, in those days it was the Nuclear Institute, Saha Institute of Nuclear Physics. And it was inaugurated by this lady. Who was this lady? Irene Joliot-Curie. Who was Irene Joliot-Curie? She was the daughter of, right. I met Irene, I didn't meet her. I saw her, I should say. When I was in 1947, there was an Indian Science Congress. I was a student, and all students had their duties assigned for the Indian Science Congress, and my duty, along with many others, was to usher people into seats. And Irene Curie was one of them. Another one was a grand old man, a biologist, what was his name? Darcy Thompson, a marvelous, he was in his 80s, very old man, and flowing beard, tall, and when he gave a lecture, this is nothing to do with the subject, by the way, you may be amused. I was stunned to see him draw. He was a biologist, great biologist. He would draw a picture of a bird with both hands simultaneously on the blackboard. Beautiful. So anyway, so that was Joliot-Curie, all right? And she opened the building after it was finished in 1950 or 51, all right? Then this is a picture of him. Now I come to the last picture before I go to the physics subject. This is a great, one of the 2 or 3 books he wrote, but this is a great book, Treatise on Heat by Meghnad Saha and Srivastava, one of his junior colleagues. And I am particularly showing this book because, you know, as a teacher, all my life I've been teacher, I used to loan books to students freely. That's what books are meant for students to read. And of course, many students didn't bother to return them. That doesn't matter if they read them. What what used to worry me was they probably stayed in their bookshelf without their reading them, okay? This particular book, I had a copy of it when I was a student in BSc Honours, Treatise on Heat. I lost it. Then when I became a professor in Jaipur, I bought a copy. I again lost it. So I finally decided Lokanathan and treatise on heat were not destined to be together. When Pramod said I should give a talk, I accessed amazon.com and saw whether I could get another copy. And lo and behold, it's not available. Do you have one in the library? You should have one. All right, try and get one. It's a great book, very great book, one of the beautiful books. Absolutely, you should all see it and read it. Okay, good. All right, and all right, just two more and then I will get back to the other subject. In 1951, he contested the elections. What happened in 1951 elections? That was the first general election, thanks to Jawaharlal Nehru, all right, and others. And our friend Meghnad Saha was now such a big man, he could easily have become a nominated member of Rajya Sabha or whatever it is, etc. And maybe other parties would, all parties would have had him as a member, but no, he contested as an independent member because he had the spirit, because he wanted to be independent from a North Calcutta constituency, and he won. And he became a member MP in 1952 of the Lok Sabha, not just as a scientist, but as a man who wanted to fight for science for the people. And he differed from Nehru, he had differences and so on, and he would be frank about it and so on. Great man, great spirit. Suddenly in 1956 he died of a heart attack, all right, and that is the man, all right. So in my last part I am going to tell you what is the physics of this so-called Saha equation. Okay, do you have any questions about this so far? No, or you can ask later. All right, what did Saha do? Okay, in now, you know, the history of science, if you look at it, the pace of research changes rapidly, suddenly, because of either a new discovery or a very unusual development in instrumentation. For example, it was naked eye astronomy in the ancient days, and you know what happened when a telescope was discovered? Galileo made himself one, and you know what Galileo did? I'm not going into that, okay? So, as telescope changed the pace of astronomy. In 1835, I've written 1935, wrong, 1835. In 1835, a French philosopher who was also supposed to be the father of sociology, called Auguste Comte. And this is what he wrote. By the way, those were days when philosophers had much to say about science also. Sometimes sensibly, sometimes they talk nonsense. Auguste Comte said, I regard any notion concerning the temperature of stars as forever denied to us. All right? And I have written here to tell you, never say never, especially when it comes to science. All right? I haven't seen a movie for ages. My grandson told me that there is a famous James Bond movie, is it? Never say never or something? Never say never. All right. So never say never about science. Because within 10 or 15 years, August Comte was proved wrong. Why? Because Robert Burns and the famous Gustav Kirchhoff discovered a fine thing that when things are heated, metals or something, they show characteristic spectra from which you can identify the materials. So you can use spectral lines to identify materials. All right, this opened a new area. But that was not alone. Spectroscopy had developed rapidly because of gratings, all kinds of things, I don't want to go into it. But spectroscopy would only tell you the frequency of the lines, all right? But if you want to know the intensity, there was an additional thing called bolometry. So there are spectroscopes. By the way, what is the difference between Shailaja, I learnt this much later in my life. What's the difference between spectrograph and spectroscope? I learnt that spectroscope is what you see and spectrograph is what you can't see. Non-visible spectra. I don't know. Anyway, I call them all spectroscopes. It doesn't matter. You can educate us later. Spectroscope was allied to bolometer. Bolometers, I won't go into the physics of it. You can also study the intensity of the lines. All right? And that gave a new impetus to a new subject, growing subject, quickly growing subject called astrophysics. So astronomy grew into astrophysics rapidly. And that was the atmosphere in which, I will skip, atmosphere in which Meghnad Saha found himself in 1917. What did he know in 1917? All right, again it's my conjecture. He knew that in 1900, Mr. Planck, or Professor Planck, had discovered his famous black body radiation formula, number 1, which showed not much for him, but for Einstein it did. So Einstein reinterpreted Planck's formula as though light also consists of photons, etc., because he had also done something called photoelectric effect, etc. Okay. So number 1. Number 2, Rutherford came up with the nuclear model. Number 3, Niels Bohr came up with his famous quantum theory of the atom. All right? So these were 3 great things he had before him. So the crucial thing about Bohr was that by now it was clear that the atom had discrete energy states, and number 1, and the second important thing, Bohr said many other things which have gone by the board. You don't like them now, you go into quantum mechanics, that's another story. But the 2 things that Bohr did that still stays with you, atoms have discrete energy states, and when they go from one energy state to another, they either absorb or emit a photon. Okay. So these things were familiar. All right, and S.N. Bose used them in a different way. I won't go into that. If I am called upon to give a lecture on S.N., somebody else will do it better than me. S.N. Bose will. So today's S.N. Bose also did some brilliant thing, but that was another story. Our friend, I am now talking about Meghnad Saha. So now in 1917, just before, Einstein came up with another brilliant paper. I want to tell you something about Einstein's paper. Right? When there are papers written by other people, I won't mention names because they will get angry. When papers are written by great scientists, they read them in order to impress how great they are. Right? When Einstein wrote a paper, He wrote because he wanted Lokanathan to understand it. And you. So, never ask Madhusudan or Shailaja for Einstein's paper. You read it yourself. You will enjoy it. It's like Aesop's fables. Einstein's papers are a pure delight. All right? You should read them yourself. Now, in 1917, he wrote a very great paper. It's called the A and B coefficients. And that I will tell you in a little detail. So, what happened was that Einstein asked, if you had several excited states of an atom, how are they populated? If you have a large number of atoms, how many go into the ground state, how many in the various excited states? There was a famous thermodynamic law due to Boltzmann long before. It is called Boltzmann's canonical law. Do you know what canon means? Canon means God gave us, don't ask me. All right, by the way. So canon, church canon. That's how it is descended. But physicists use these words a little bit humorously. So it is called canonical law. And you also have Hamilton's canonical equations, etc. Really, when we want to impress you students, we call them canonical, okay? Okay. So, canonical law of Boltzmann said that when equilibrium sets in, then the population goes as e to the power minus E upon kT, E being the difference in the energy. So, if you have 1, the next one is e to the power minus E upon kT, E being the energy difference. All right? K is Boltzmann constant and T is the temperature. All right. I can, by the way, if I had time, I could have shown this very trivially. The proof is not difficult. I didn't invent it, by the way. I knew this because others had done this before. All right. So, what has this got to do with it? All right. Einstein did something very clever. He said, all right, let's consider 2 states. I have drawn them. On the left side, you have a photon. What happens? There are photons around and there are these atoms. And one possibility is a photon of the right energy between these two hits a ground state atom and shoots it to the first excited state. That's called stimulated absorption. All right? The second one is, if it is already excited, it will spontaneously, it doesn't need anything. It spontaneously comes down to ground state, emitting H nu. But the third one is also very interesting. If it is already in the excited state, then the ambient surrounding photons, one of them, if it happens to be the right energy, will tickle that excited state in order to come down. Right? So, you will then have 2 photons, one which tickled and one which was tickled. Is that clear? So, both photons. That is called stimulated emission. Right? And yesterday or day before Nobel Prize, laser is a consequence of this stimulated emission. All right? Okay. So you can thank, like most things, you can thank Einstein for everything, right? So this was, now what he did was, Einstein argued with these 3 processes taking place, you have the system. You have atoms in ground state and various states. You have the ambient radiation all in a box at a temperature T, and they should all be in equilibrium. And he showed that this equilibrium automatically will give you, he wrote down the equations, I'm not going to do the physics. I'll send it to you if you want. The you read the, you shouldn't ask me, ask Einstein. I said, go to YouTube, access this, read it yourself. So he showed that Planck's law follows from this balance automatically. Another thing that followed was E2 minus E1 equal to h nu, which Niels Bohr, one of his postulates, follows. The third one was that he showed that everything was consistent with a photon being emitted or absorbed in a particular direction and carrying a certain momentum. So the photon now became a respectable particle. All right? Before Arthur Compton did his Compton scattering. This was Einstein 1917. Now, what does all this have to do with our subject? All right. And that is the, perhaps I'll try to All right. What did Meghnad Saha do? So Meghnad Saha said, if Einstein could do that with excited atoms, I can do it with something else. What happens when the temperature gets very hot? What is room temperature? Room temperature is about 1 upon 40 electron volts. KT at room temperature is about 1 upon 40 electron volts. So ionization energies are in the region of electron volts. So you need temperatures of about 10,000 or more to ionize atoms, and that is what happens in stars. And Saha said, okay, what happens when atoms get ionized? He said, by the way, I'll come back to this equation. He said that now you have two atoms, you have more, depending on how many have been ionized. You have one atom which has lost R electrons on the left side, and you have one which has lost R plus 1 electrons, one more electron on the right side. And their energy spectra are different because, all right, because depending on how many electrons are the energy, I'll come to an example, then it will become clear. All right. By the way, the ground state of R plus 1 is higher than the ground state of the NR on the left side. Can anybody tell me why? Huh? Why? Because if you want to remove one more electron, you have to put some energy into it. Is that clear? So the ground state of the higher ionized state is a little higher. Is that clear? And here comes the brunt of Saha's argument. Saha said that energy difference plays the same role as the excitation energies in Boltzmann, right? In Einstein's AB coefficients, which I showed you. So instead of E2 upon minus E1 upon KT, you have ionization potential upon KT. All right? Madhusudan, shall I go to the previous one? There it is. Sorry, thank you. All right. And you see that on the right side, exponential minus chi r upon KT, that chi r is the ionization potential. All right? There are other factors. On the left side, you have the occupation numbers, nr plus 1 upon nr, times Ne. Ne is the electron density. The electron density plays the same role as the ambient photons. There you had black body spectrum as the ambient radiation. Here your ambient thing is the electrons. Is that clear? So the electrons can either be absorbed or more electrons can be created. All right? Electrons, by the way, electrons don't get created out of nothing. They come from the atoms. Whereas photons, that's another story. I shouldn't go into too much detail like that. Okay. So you see the connection. On the right side, you have other factors like G. If you are very fussy, I will tell you what they are. They are called statistical factors. Okay. And I will skip them. And then you have 2 pi mkt raised to the power 3 upon 2 upon h cubed. That has to do with the phase space and all that. All right? You need some work to do. So go home and read. All right? So that is the full equation. So this is what Meghnad Saha did. He enlarged the scope, but then it was a very important discovery. Why was it a very important discovery? All right, I'll give you an example. Supposing you had helium in the star, neutral helium. How will you see it? Its excited states will give you helium spectra in your spectrograph or spectroscope. Then, if helium loses an electron because it gets ionized, then it has only one electron, it becomes exactly like hydrogen, so its spectrum should look exactly like hydrogen spectrum? Not quite. The hydrogen spectra are spaced like this, the helium spectra are much closer spaced. Why? Because the nuclear charge of helium is 2. So the energies are much closer spaced. But this is very important. From the spectra, you know how much helium plus helium ionized is there and how much non-ionized helium is there, and from that, using Saha's equation, you can deduce the temperature. All right, I'm oversimplifying, there are other things to do. Is that clear? And they used it. And I am told, I am not an expert in this, they found O stars were found to be hotter than B stars. The common stars went by the name of O, B, A, F, G, etc. Why these letters? You can either ask somebody else or ask the expert here, Dr. Shailaja, not me, I don't know. So, all right. So, the point is that this was apparently the O stars looked yellow, am I right? The O stars looked yellow and they thought it was colder. And it turned out that O stars were hotter than B stars. This is one example. And many other things were done. All right? All right. Sorry, I'll finish in 5 minutes. Is that? Yes. So, if this is that good, why did Saha not get enough recognition? When I was in Delhi University as a student in the 1940s, we used to do the same things as you people do. What? What will be the questions in the next exam? Right? So we used to do our guesswork out there. And Saha equation, it must come this year. It hasn't come last year. And so on, so on. It was very important for us, Saha equation. We were geared in Saha equation. All right, I finished my MSc. I went to Columbia in New York. And to my astonishment, I had friends, classmates, who hadn't heard of Saha equation. And worse, there were textbooks which did not mention Meghnad Saha. And even worse, the few textbooks that did mentioned it as Langmuir-Saha equation, which annoyed me, which got my blood up. Because good old Langmuir, he did many things, by the way, good things. In fact, what this ambient thing that I talked about for Saha was called a plasma later. Plasma, okay? Neutrals, etc. It was called a plasma. Langmuir was the king of plasma physics. Later, 3 years later. So he came into the picture 3 years later about all this. So why call it Langmuir-Saha equation? Anyway, that's the bit. So somebody asked a Nobel Committee member, why is it not worthy of a Nobel Prize? And apparently he said, the Nobel Committee does not think it is a discovery. All right. So I wrote the following jingle. Nobel committees do not a discovery define, nor Nobel prizes the physics. All right. By the way, I didn't invent these lines. They come from a poem by Lovelace called Stone Walls Do Not a Prison Make, nor Iron Bars a Cage. These were poems which I learnt as a schoolboy. So, in my opinion, all three of them deserved Nobel Prizes. Raman got it. I think Bohr should have got it. I think Meghnad Saha should have got it. Okay? And I think the work was a great piece of work. And however, that is my judgment, others may differ. And I think I should stop with it. And then, oh yes, I stop with it. And as an old man, I will end with this wish that you can make up for it if you REAP students win so many Nobel Prizes to make up for all this, okay? I'll stop there. Thank you.